All right, looks like we're ready to get started. Kind of banging around a bit. It's class time. Sorry. So today we're going to talk about system ID from transient, and more specifically, the step response. Then we'll have an in-class exercise, which will be system ID from a Bode plot, and I will, randomly assign breakout rooms, and then I'll try to monitor everything. And then we'll kind of come back and refresh that. Now, before we get going, are there any questions? Okay, just so you know that you don't really have to make an official appointment through Spartan Connect. Really, just email me, we'll arrange a time, and we'll open up a Zoom session and go from there. I'm pretty flexible. I just can't make it when I'm eating or at my virtual karate. All right. So there's something interesting. One, I learned how to draw a straight line. And smooth draw here. But besides that, is that we have the time response, and let's just, say that it's an RC filter. And, that's my approximation of 1e to the minus t, right? ut. And that, it takes 5 tau to get up here. But then when we look at the Bode plot of that, right, we have something that starts off at what looks like 0. Now it's 0 dB, and then gets smaller. And it almost looks like these are the inverse of each other if you flip them around the x-axis, right? I have a shape that does this, and then I have a shape that does that. Now, yeah, this is rounded because it's exponential, but remember in our Bode plots, asymptotic Bode plots, we tend to draw things, with a, kind of an angle. And of course, let's not forget the phase. All right. So the thing is sometimes you can forget that or get confused about these shapes. And there is a technique that you can mathematically figure out if you have the transfer function, you know, what the beginning and the ending should be. So let's just say we have a function of time, right? And we can also have it in the S-plane. All right. So if I multiply this times S, and as the limit of S goes to infinity, we get X at time equals 0. Where this is exactly in the book is in the module 6 activities, and where I told you to read it. And I just put it up there yesterday. But so let's see how that would work. So the transfer function of that low pass filter is omega naught S plus omega naught, which doesn't do much on its own, right? So let's say we want to take the step response. Okay. V out equals 1 over S times H of S. All right. Well, if I want X V out T equal to 0, that will equal 1 over S times the transfer function times S, and let S go to infinity. So we're right back where we were with the transfer function. All right, we let S go to infinity, and we get omega naught divided by omega naught. No, sorry. We get omega naught divided by infinity plus omega naught, which gives us 0. All right, and so let me try to. So that 0 gives us that point right there. All right. Now, now what if we want X T going to infinity? Same thing. S times whatever signal of S, but now we let S approach 0. So I'll do it again as V out as T goes to infinity, right, will be S times omega naught, S plus omega naught times 1 over S, because we're talking about the step, right? Again, these S's cancel, we're left with this. So as S goes to 0, omega naught divided by omega naught goes to 1. All right. and that's 1. And what is considered infinity, right? T greater than 5 tau is considered infinity. So this is a formal way of looking at it, but here's maybe a more intuitive way to help you. Okay, here we have time, and here we have frequency. And what's going on in the early shows up in the later frequency, right? And what's happening later in time shows up at the lower frequencies, right? So time, frequency, low pass does this. That's that. That's omega naught. And this is 5 divided by omega naught, where tau equals 1 over omega naught. Okay. Now, how would this play out in the high pass? Okay. H of S divided by S plus omega naught. We want to find V out T at 0. That means we get the step times H of S times S, which cancel. Since we're looking at 0, S goes to infinity. We get S divided by S equals 1. T going to infinity. Now I'm just going to use, and this is only true for step functions, right? In fact, if you were going to use the impulse, that would be different, but it's pretty convenient to use this for a step function where S goes to 0. We have 0, 0 plus omega naught goes to 0, right? And so transient response to a step, that's 5 tau, or 5 divided by omega naught, that's 1, that's 0. And that's omega naught, right? So this portion in time shows up here. This portion in time shows up there. Any questions so far? I think just something to remember is even though we're doing system ID, right? From a transient. And you might be thinking, well, I should be looking at E, looking at this, or, looking at that. This is what you're seeing, but really the system we identify in the S domain, and in fact, you do both, right? You have an idea of what things are to go from there. I see your question. Just somebody had an email question I better get to. Nope, not important. Right, that's exactly it, Mark, and I think that's a good segue into these more formal notes, all right, where we kind of go, we use both. And actually being able to go between both the time domain and the frequency domain, it's really important. Sometimes people who are just learning this sometimes think like there's two different things. There's one system for the S domain and one system for the time domain. They're really the same system. There's just a different equation describing what's going on, but they are the same system. Sometimes what happens is we start in the time domain in our circuits course, then we look at it here, but then we spend so much time in the S-plane that we even forget time exists, okay? So let's just do some simple first order things where integrator is a first order system, right? And if I do the step response of that, right, it turns into an integrator and you get a ramp, which is the blue line, right? And then a differentiator is taking the derivative of that. That's this line here, which is just S. When you take the inverse Laplace of that, you're just taking the derivative. Here, when you take the inverse Laplace of that, you're just taking the integrator. I do have these links to Desmos for you to look at. All right. So now let's look at so we have these high and low pass filters. All right. Let's see if it opens up, because I think I have it as an animation. Sorry, I wanted the transient. All right. And so here's our omega naught, and you can see that as it's getting bigger, things decay faster. As it gets smaller, it decays or rises more slowly. All right. But to take a look at that and say, how can I tell that this is a first order system? Is that it really starts increasing right here. There's nothing, there's no delay, and there's no ringing. Okay. So you have to kind of assume, yeah, this is a first order system. And then what I would do is just calculate how long, what was 5 tau, right? And then the gain, if I put in a 1 volt step and I get 1 volt out, then the gain is 1, right? And I find 5 tau, which then I can find omega naught, and then I've described the system, all right? But this is really just to give you a feel for what it looks like when you're changing the time constant there. All right. Now, here we have second order is, let's just say it's a bit harder, okay? In that the Bode plot, it's easy to tell. All right, it's low pass. We can see 2 well-defined breakpoints, so it's overdamped. Here we kind of looks like 1 point. You'd have to extract it to know that it's critically damped, but with this peaking, you can definitely tell that it is underdamped, right? And to take the inverse Laplace of that, you have to know what your roots are ahead of time. So if you have 2 real roots, right, you calculate your poles according to this equation, right? Here, if you know your poles from here, that they're repeated, you use this equation, and then here, this is for the underdamped response. Now the thing is this is about the transient. Here's the thing. This one you can tell it's underdamped and that it's definitely underdamped second order system. These are a little bit harder. I know that there's this little bend here because, you know, I did it. But for you, you really couldn't tell if that's first or second order. And that's what makes it difficult to do these. So when we're talking system identification from a transient, it's much more descriptive and less analytical as doing it from here, where you can get a pretty exact result. All right. For the high pass, again, we can have under, critically, and overdamped. Now, what's interesting here is that the critically damped, it looks like it's ringing, but with a high pass filter, it can go below once and settle, and that's critically damped. And then if it just never goes across, that's actually even overdamped can cross that line a little bit. So it's really difficult to look at a high pass filter and see that in fact it's extract the values for it. But you can definitely tell that it's detecting an edge and it's just taking a certain amount of time to get back to zero so that it's a high pass. Band pass, a little trickier, all right, because in some cases it looks just like a high pass filter. And when you have two roots, right, because the damping factor is really large, all right, you'll have one root or one pole much bigger than the other. The large pole will decay so fast that you don't notice it. And so the reason why it looks like a high pass filter, right, because if you notice, right, this is looking low pass, this is looking high. It, like the notch filter, it's got both, it's just the order is rearranged. But what it is this low pass pole is so much bigger than this, right, that this is dominating how long it takes to decay. Now, when it's critically damped and they're about the same, notice right in here, it doesn't go straight up. It's a little bit, it doesn't start at 1. And notice this doesn't start at 1 either, where with the high pass, it goes right to 1, right? So it's a little bit reduced. It doesn't, it only shows ringing when it's underdamped. All right. But yeah, at this point, it's somewhat, the difference is this goes to 1, this doesn't, all right? And the fact that you see this space in here is really telling you that it's a bandpass. The notch, well, it's got a high pass and a low pass, except the low pass comes before the high pass this time. And so what might be hard to see is that it's trying to go to 1, or it does go to 1, and then it drops, and then it goes to back to 1. All right. So again, with the notch, because you can see it right there. We have a high pass added to a low pass. Here's our high pass, right? And here's our low pass action. Where with the band, the high pass is happening at lower times, and actually it's actually starting at 0 in both cases, rising and falling back to 0. Here it's starting at 1, dropping and going back to 1. All right. Oop. I just saw your chat there. frequency bandpass. Let's see. So maybe instead of H or frequency, I'm saying, oh no, I'm saying function of time. The high pass function. Yeah, you're right. That's totally right. That should say notch. My bad. Oh, good catch. Ah, okay. So up here, what the question was, what do those colors represent? And the red is with a damping factor of 10, which means there's two distinct real poles. Damping factor of 1 is critically damped, and that's in blue, and green is underdamped. So in all these examples, it's all the same. And every time there's a color with an equation, okay. Now, okay, good. So, how this might work, right, is if you took 110 this semester or last semester, 110 lab this semester or last semester, you did do a first order measurement of a Bode plot, right? What this is a second order Bode plot from measured device. Okay. So this is actually measured data, and you can get a feel that the phase is a bit noisy. And phase is actually hard to measure because you're, rather than taking a voltage ratio, you are trying to, where's my, sorry, this is, you're actually measuring time difference in the length of the cables, and the capacitors that are inherent in the cables can make it really hard to calibrate. All right. But anyway, this is a second order system. And so a quick review on system extraction from a second order Bode plot, right, is that the gain is 0, and I just would draw an asymptote this way. And then I find where my gain is constant slope, draw something up here, pull down, and I get a cutoff frequency, all right, which is about 350 kilohertz. You might think, well, wait, why not just take it where the gain is minus 90? But there gets to be a lot of noise in here, and this asymptotic method is a little more accurate. And what the phase is actually telling you, because it's going negative, is that the transfer function is not inverted, right? If it was going from 180 down to 0, you'd know that there was a minus sign in front of it. All right. Oh, hey, Ed. What's your question?
Hi, Professor. So what do you, I'm still figuring out this system ID. So is is it given that it's a second order system, or do you have to figure it out from the Bode plot?
You kind of assume that you don't know anything. And so there's two kinds of system ID. You've measured a Bode plot, right? Or you're looking at a transient and trying to see what it is, right? If you really want to know what the system is, you kind of have to do a Bode plot. But when you're doing, sometimes you're just testing a system and trying to identify what's coming on. And why you need to know both, this example right here is about to show you. All right. So anyway, I calculate the cutoff frequency of 350 kilohertz, right? The DC gain, I can see it's going to 0 dB, so that's 1. Omega naught is 2 pi times the cutoff frequency. All right. Now, in order to find the damping factor, I need to know what the magnitude is at j omega naught. So now I come back up, read here. And it was minus 5 dB. So when I calculate that out, it's 0.56. When I put that in the damping factor, I get something slightly underdamped. All right. So great. I have identified the system from a measured Bode plot. Right. Let's keep going. Well, now I want to kind of match whether that's working or not. And so what I did is I had an RC circuit, and there's component tolerances that come in there, and you put in the generic ones. But again, resistors aren't always what it says on the label. Same here. And so what I did is, this was the system response that I extracted, right? And then, so V2 is this, and what you're not seeing is that this VFR, right, is what this equation right here. And you can see that it's matching pretty well. But I kind of had to tweak it. Even then, I had to adjust it a little bit after the fact. That's that's more advanced. It's not part of this course per se. All right. Then I look at the transient response. And even though the damping, so how could I tell that this is a second order system? Well, it's not a straight line up from here. But if you really look at this, you can see that it's coming up just a little bit. Because remember, our damping factor was 0.89, right? And you can see that it does rise up a little bit, all right? And so I'm getting this to match. So the Bode plot is working, everything's working, right? Well, then I go, instead of measuring it sine wave by sine wave, I put in a step function. And yellow is the output of the function generator. And I don't know if you noticed, but that doesn't look like a step, right? What is that, right? Oh, this looks like a step response of a low pass filter, but that input does not look right. Okay. Well, what happened? Well, I'll tell you. Is that R1 was 75, and the function generator has an internal impedance of 50, right? So in fact, you're getting a voltage division, this FG out here, right? Which when you calculate that out, you in fact get a notch filter, right? Now you don't want a notch filter. So the thing is to make R1 a lot bigger than RS, okay, which we talked about around the middle of the semester. But what I thought I was just going to do a simple example for the, oh, here's an RLC filter. And if I didn't know what this shape was, I would have had no idea how to debug what's going on. Now, here's the thing. Why did the Bode plot work? Well, in the code, it takes your V out and divides the amplitude of V out and divides it by V in. So even if as frequency is changing, V in is changing, it doesn't matter. V out is just being scaled by it. And so the Bode plot kind of masked the issue that this wasn't really. So even though everything was great, and I could have used this for a pulse width modulated filter, it actually is a terrible pulse width modulated filter, but it only showed up in the transient. All right. But okay, so here's the thing: is that really to get a decent model, you really want a Bode plot because you can look at all the different frequencies, but it can, you're checking each frequency, right? And if you're doing something with time constants that are like 10, right, or a millihertz or 10 millihertz, right, it can take a long time to do a Bode plot. So if if something has a time constant of 1 milli and you want 10 periods of that, it can take a long time, right? Another thing is that with the step, all right, I can take the derivative of this, right, and plot the fast Fourier transform of it, and it turns it into a Bode plot. So imagine, rather than all different sine waves, I put in a square wave, take the derivative, take the fast Fourier transform of it, and I get a Bode plot. The trouble is the input would be this, right? So, square waves and step functions are in your future, and you have to kind of notice what's going on. All right, but that's kind of how it's used. Now, yeah, a lot of times I left the notes here. I left the notes here. Oh, wrong one. Okay. So the thing is I do have examples. Right. Right. And this is really a summary of what I just said, is that you can do a square wave and use an FFT to rapidly test your system, right? But I have examples of how to extract for first order system. But second, so here's the thing, even though I did this example, right, it is really, really hard to extract a second order system because you have to assume one pole, and that's all this plot is. I've assumed one pole, and then I'm sweeping and I'm sweeping another until I get the right shape. Okay, which is so in this case, I know it looks like the other ones don't match, but why this line of -2 is the best one, it's just really hard. I'm not telling you to ignore ignore these slides, but yeah, it's more trouble than it's worth. So really, when you look at what are you expected to be able to do besides the homework, right? Is it first or is it second order, right? Complex poles or not, right? It can be really hard to tell over or under damped, right? You should be able to see filter shape, right? Low pass, high pass, low, high, band, notch, right? And these are all function. So is it a low pass? Is it high? Now, yeah, of course, low and high can be first order. These have to be at least second order. So you could see if this was second order, you might see some ringing, right? And there's something, where did it go? That let's say we're looking at something down here, it's got minus 40 dB per slope, right? That means it's second order. And then you extract this and it's minus 3 dB, and you're thinking, oh, that's sometimes people see that F naught is that gives you minus 3 dB and makes you think it's a first order system. You really got to look at the phase, right? Is it going towards minus 180 in this case or not? Or in the other ones, you're looking for a change in phase of 180, right? But this is minus 3 dB second order. The damping coefficient is 0.707. It's complex, and that means you will see some ringing. So just because there's no peak here doesn't mean you won't have ringing there. Any zeta less than 1 will have a peak, okay? And this is low pass step, all right? So now, yeah, if this has this kind of shape, this will really go like that. But what I notice is sometimes people confuse or forget that a peak here, yes, will guarantee a peak here, but a non-peak, it'll still could be a peak. In fact, for critically damped, if that F naught occurs, right, and again, that's minus 40 dB per decade, occurs at 6 dB, that's critically damped, okay? And then, of course, if you, they're going to use this. So I come here, right? I have one break, and I have another. That's two separate poles, right? All right. So what I would like to do is we've got 49 participants, and I'm going to assign you into breakout rooms, right, where you can work on I set up an assignment for you. So log into Canvas. Now you can, so I want you to work on it together, but each person will see a slightly different question. So you want to submit your own answer, right? And you can do it as many times as you like. I see you, just let me get to, so if you go to module 26, right? It's M26 in class group assignment. You load it. I see your questions. I'm just, and there's just one question there that you have to do. All right. Okay. Oh, assignment closed. Okay. There's probably a problem in my open math. Says it's closed. Just let me see what I messed up. Because of course it worked for me. Anyway, we'll give more time. Yeah, that's what I figured. Let me go fix that. You know, I'm sorry. Okay, so that should be good. Assign 49. No. Into okay. Maybe some, I thought there was, oh, I'm the 49th person. Okay. So it's groups of 2. I'm going to open all the rooms. You've all been invited. Everybody's leaving me to go to their room.
Professor, I just have a quick question.
Sure.
What does a V over V mean? Like approaches V over V?
Okay, that's this weird thing. Hold on. I don't know. I think so. V over V just means voltage over voltage, which means it cancels out, but that's trying to say it's not in decibels. You'll see it on op amp data sheets.
I just know
Okay.
it's not decibels. Okay.
Yeah. Sorry. All right. So Ed, yeah, you go and sign up. Adam L, Arturo, Edward. We still have a few people who need to join their room. Okay. Funo, Mark, Adam, Arturo. Hiromi, I still see you. Join your room. Edward, your teammates are waiting. They're going to be lonely. Ed, you got to join. Budaman, Edward Lee is lonely. Edward Budaman, you still there? Zhuzi Wang, you need to join your groups. Let me send you a chat. Start recording again.
Okay.
So visually inspect and tell me and see what's going on. That to me is a very authentic task. Oops, gotta keep trying to kill it. Oh, share screen. That's what's going on.
I don't know if you did this intentionally, but you're muted right now, Professor.
Man, there is something about being a professor and the mute button that it's just like, and I laugh when I read about it on Facebook.
Happens
That's
to
not
everyone.
all right. Well, anyway, thanks for telling me right away.
Yeah.
So, you see how this is shooting straight up? That's that classic this kind of equation. Starts low, goes high. So it's passing the DC, right? So that I would say, yeah, that's a first order low pass filter. And because you could get 5 tau and the gain, you could get that equation. First order, it's relatively straightforward. And then for the high pass, Oh, I went and did it even like more exacting, but the high pass is the same thing. As you just see 5 tau exponential, right? So where's oh, I see it. Sorry. Okay. Oh, there's a chat. Or not a chat. Okay. So here you can see the Bode plot and the step response. And the fact that it's low pass, you can still see that. You should be able to identify that. This one, is it critical or is it underdamped? Well, you know that it's overdamped because I'm telling you that's critically damped, right? But if this red plot was there with no other context, it's very hard to tell if it's critical or overdamped. Because if the poles are so separated, the slow pole dominates and makes it's impossible to see the fast pole. All right, but you can definitely tell that this is a underdamped second order system. So that's like an inspection. Here, right, it passes that first edge and decays to 0, high pass. Now it's a little trickier in that the critically damped and even some of the overdamped will pass this line, right? So that's, but you should be able to tell, you know, when I do things, I do try to make it obvious that it's really ringing here. So it's really underdamped. Now the band, notice that we have a slow pole and a fast pole. That slow pole is dominating and it almost makes it look like a high pass filter. You can barely, the only way you can tell is this little tiny thing here that it's not going exactly to 1. But in here, you see it starts up, if you zoomed in on it, you can see it starts at 0, goes up high, right? And with the notch, yeah, it passes that high passed edge here because it's detecting the edge, but then it passes the DC here. So it starts at 1, goes low, goes high. Where here, it's obviously kind of slowly rising to a value and falling back down, where the high pass, it almost instantaneously goes up to the high value and then decays. All right, so just we're looking at, you know, is it likely that it is underdamped? Oh, very likely. All right, in here, it's a little harder to tell, but you should be able to see high, low pass and notch. Okay, you should be able to do that. And yeah, if you go look at the questions and the homework, and even on the final exam, you'll see that it's, I'm not asking you to find all of these values from the transient. It's, what I end up doing is I make an assumption, plot it against what I'm seeing, and then start tweaking to get it right. All right. And then, you know, like this is a real world task because I had a Bode plot. But then when I went to measure it, the input wasn't a step, but it was jumping out at me that it was a notch. And that made me realize, oh, I'm getting a voltage division here. If this resistance was 100 times this, that voltage division would still occur, but you wouldn't really notice it. So in fact, these notes came before the lab exercise where I have you, I'd show you what happens when these two resistances are the same, a little bit bigger and a whole lot bigger. And when I talked about that RLC circuit where I wanted this like 2K or bigger, right? It's because of the function generator. Okay. Just gonna see. There's a few people still in their rooms, which is good. But, God, I hate to just throw people out if they're having a good conversation. But I think I'll just give a warning, and then they can meet up later. You guys have access to Zoom as well. Are there any other questions before we go?
Yeah, I had one in the chat.
Oh, you do? I don't know, chat. Can you just ask it? I can't.
Yeah.
I just, my chat isn't, I don't know.
I'm glad you said it.
Okay.
So for finding omega naught for a bandpass, is it a quick way to finding it by looking at the peak and then the frequency?
Yeah, I tried that. No.
Ah.
No, what I thought I was, where's my smooth draw? Okay. Oh, there it is. So finding omega naught on a bandpass from the Bode plot, oh, that's not a problem, right? In fact, okay. So the bandpass, notice we go from, it's a change, everything's for second order, everything changes 180, but here we start from 90 to minus 90, and so omega naught is always happening at 0. Now these are in last class's notes. So see, it's omega naught is all 100K, right? For the notch, you have the discontinuity right at omega naught. For the high pass, omega naught, you can say is always at plus 90, and the low pass, it's at minus 90. All right. In this case, I could also find it by stretching out the magnitude and reading it that way. Same thing. For the band pass, it's just kind of the one in the middle. Oh, I got 3 chats, which I think it's when okay. Okay, Diego, I'm sorry. I don't know what I said. But yeah.
Thanks, yeah.
Yeah, okay. But good comments. All right. I'm just going to send a chat. Okay. Sorry, I do have a birthday Zoom meeting for my father that I kind of have to get ready for. All right. So everybody stay safe. If you liked it or didn't like it, or have anything about how today's breakout sessions work, could be done better or could be done worse, just let me know. I'm really open to what you guys have to say, because it's really kind of new for everybody. All right, take care.